Hello guys, today I'll show you how to solve the sum problem. I'll be showing you the recursive approach, which will time out, and I'll also show you how to convert that recursive approach to a dynamic programming tabular method. So for this question, we're given a list of non-negative integers and a target s. So for each of those elements in the array, we can either give it a plus, give it a negative, right? So if you think about it, so given the first element, we can say, okay, I can choose this to be a +1 or -1. The second element, okay, given to what I have chosen for my first element, my second element will also be a +1 or a -1. Then that just kind of naturally forms like a decision tree. Like from your root at the top, from the first element, you branch down to other decisions. For every element, there's 2 decisions. So we can form a tree structure, right? And whether or not we know if we can form a target sum from the entire array, we can say that when we reach the end of our array, if our target sum, or the sum of all the elements we have choices we have made so far, add up to the target, or if you think about the other way, if we cumulatively subtract our chosen symbol from the target value, so at the end, if we reach the target of 0, then we have successfully reached our target value at the top, right? So if we draw a tree, it would look something like this, right? So given an array of 1, 1, 1, so 3 elements in the target of 3, we start with saying, okay, I have chosen my 0th element and I have the target 3. Now let's branch, right? I can choose -1 or +1. If I choose -1, then I branch into this other tree, which says, okay, now I have chosen -1 for my first index. Now I need to choose for my second index, right? And for my second index, I can choose -1 or +1. And notice that how here the target we deducted 1, because at the end we want to check, after we try all the choices, at the end of the array, do we have the target of 0? If the target is 0, then we have successfully found a path, right? So you can actually think about this as, for all the leaves of this tree, we want to sum up of all the leaves whose target value is 0. So in this case, we see that we only have one such value here, right? Which is our base case here. So let's show how this works when we code it. Yeah. So we know we have a base case, right? Let me define a new function. Just call this a recursive approach. So we have noms and the target as, right? So our base case, right? Our base case is if, and also we need an index here, right? Because we need to track which index we're at which level. So if our index surpasses our array length, right? That's our base case, because we don't have any more symbols left. So at this point, we need to see, okay, is our target 0 or not? If it's 0, then that's one path. If not, then there's 0 path, right? So when we hit our terminal case, the base case, we're going to say we return 1 if the target is 0, else we return 0, right? And now time for the binary decisions, right? So we want the sum. So each of these nodes in the tree are how many ways we can form this target value from its subtrees. So in this case, it will be how many values can we form, how many paths can we form from the target value of 2. So for our binary tree decision, we just simply do return recursively the next in the next index, the next choice basically, and we're gonna subtract our current chosen value, right? So for the first choice, this is if we choose a positive symbol. And so we subtract the positive symbol from our target value. And now we want to do a second choice, right? So our second choice is we choose the negative symbol. And double negative makes a positive. So do the same thing here. And we have target plus the index, right? And that's it for your recursive approach, right? It's a very simple binary tree. And naturally, we will sum up all these values from the bottom up, and then the root will contain our answer. But you also realize I marked some of these nodes as red, right? Well, that is because if you look at it closely, all these nodes are replicates, are duplicates of each other. So the dynamic program approach is going to allow us to sort of cache these values. So then instead of branching down more further, if we know that we have already pre-computed this value here, we can just reuse that. So you can imagine we can prune out this entire tree red here by using dynamic, right? Now, how to turn this into a dynamic approach, right? I'm going to show you how to use this exact recursive formula to directly map to a dynamic programming formula, right? So we have a DP and we have the target, right? So here's how it's going to work. Now, same problem. So if you realize in this problem, we have two sort of state that we need to keep track of. The index that we're on and the target value, right? So for the DP to work, we need to pre-compute all the possible values, all the possible choices for this particular index, and basically all the possible values of the target, right? And the target can be very large, right? The target technically could be infinite per se, but given our problem's constraints, right, we can also utilize these constraints as well. But I'm going to show you how to not use these constraints and use another constraint instead. So these constraints does not even apply to this question. We can ignore these constraints to create a more generalized dynamic program approach. So we know that the maximum sum for all these numbers, right? We by just summing it up. And we know the minimum limit, the lower bound of that limit, by turning everything to negative, summing it up, right? So we have a limit for our target. So instead of infinite, we can limit it to the negative of all the sum and the positive of all the sum. So in this case, we'll have this limit of -3 to 3. And then, so that will solve that problem. And for index, it's pretty straightforward. We know the array only can have so many elements. So we're going to say it goes from 0 to the length of all the elements. And we have an extra index here just to take care of the terminal case, to take care of our base case, right? We want to add that here to sort of map this into the DP program. Okay, now we know that. Let's kind of think about how the table will look. So initially, if we just did this, initialize the variables, we have a 2D table, right? The columns are the target limits, and then the indexes are the rows here. You can switch it around, the column rows, but it doesn't really matter. In the end, the answer is going to be the same. And so we know that, okay, our target is 0, right? So at the 0, when our target is 0 and we hit the end of list, we can mark it as 1. For any other value other than 0, it's 0, right? Makes sense. That's directly sort of translates into this base case. Now, the recursion, this part of the recursion will code, but essentially what that would do is it will fill out this entire table. Well, maybe not the entire, well, actually, yeah, we will fill out this entire table eventually, and we're going to use that formula to calculate our final answer, which is going to sit at the first index of the target value, right? Which is so basically that maps directly to our root. So you see how the index is 0, the target is 3, right? Cool. So let's think about how we can code this. So first of all, I'm gonna have a variable just to cache the length of the array, and then we're gonna have the max limit, right, that we talked about, which is this guy right here, right? So that problem out here, make this bigger. Let's do, so we know the maximum is going to be the sum of all the numbers, right? But since we have to account for negatives, we're going to create a DP table, right? So inside of our columns, we have n+1, because we want to create, so if the elements, remember how we said that here, we have one extra index for the terminal case. So we add 1 here. We'll create n+1 rows, and then, oh, sorry, n+1 columns. This will actually go outside of here. Okay. This is a Python's way of doing this, creating a 2D array. So, but inside the columns, actually, we want the iterate through the limits. So we're going to go iterate through the max limit times 2, because there's the negative case as well. And we need to +1 because we need to account for this 0th case here. Because if our max, let's say our max limit here is 3, 3 times 2 is 6, but we actually have 7 elements here because this is 0 sitting in the middle, which is actually going to be really useful. So we need to account for this. That's why we do a +1 here. Right, cool. So we made a 2D DP table right here. And now our base case, right? Our base case would be, and then we initialize everything to 0. So here, yeah. So basically this table will be initialized with everything at 0. And then, but we know that for this case, the base case, if the target is 0, then we'll mark it as 1. So we do exactly that. We say, okay, at our end of our row, the last row, if the target is 0, equals 1. And actually, here's the tricky part of this problem. So we actually cannot use 0 here because our table is 0 indexed. So what we actually need to do, we need to shift everything over. So this becomes 0, 1, 2, 3, 4, 5, 6. Right? You cannot index a array using negatives. So in this case, this maps directly 0, 1, 2, 3, 4, 5, 6. So we need to shift this target actually. And how do we know what to shift? It's just the max limit, right? So we can shift this by the max limit. And so that'll give our real target value in the table, right? Shifting. So basically remember to shift by max limit to move negative indices to correct indices, right? Okay, cool. So we have the whole table initialized to 0 and with the target base case as 1, right? So now we're going to go bottom up. We're going to start filling up this table. And we're going to do that by just looking at our recursive code here and do exactly that. So what do we need to do? So we need to iterate through our columns, right? Our columns here. And we need to iterate through our limit, right? We want to fill in every single option in the table here. Oops, this table here. And so we need to go from, so in this case, I'm actually going to do the minimum max limit. I'm going to negate the next max limit. So I start from the negative to the positive limit, right? Because basically in this case, I'm going from, -3 to 3, if limit was 3, right? And then we got a number to shift. So usually when you start iterating through the DP table, you need to start with something that actually has a certain value, right? So imagine if we started from 0, DP 0, everything is going to be 0. There's not going to be any value in doing that. And because we're filling it in from the bottom up, we actually want to reverse this. So we can start iterating from the last index. So iterate from n-1 to 0, right? Because then if we do dp of, so this is actually directly copied from this recursion call right here. It directly maps to it. So our dp of our current value is going to be equal to, and also have the number to shift this, right? So we have to say, okay, we'll do center this index. So it's going to be j plus the max limit, right? So the center value here is going to be the dp of our next index, right? And it's going to be its centered j minus nums of index, right? And similarly, actually this should be plus or equals to, right? Because we're actually cumulatively adding. And similarly, we can do the same for the second choice, center j plus or minus dp of center j plus nums of index, right? Do you see how these two calls directly maps to this recursive call, right? And this one maps to this recursive call. So now the cool thing is, we say, okay, after we fill our table, our answer is going to lay in, remember what we said here? Our answer is going to be laying in the 0th index in the target value, which is directly corresponding to the root here as well, right? So we need the 0 index in the target value, but the target value needs to be shifted, right? Remember I said, remember to shift this because everything's index has to be shifted. But here's a catch, right? It is possible for these values to go out of bound, right? What I mean by that is, if we look at this table right here, it is possible when we're doing this operation that, let's say 3 plus 1 is going to be 4, but we don't have a slot for 4 here. But in our case, like, right, we're going to go, like in this case, we're going out of bounds here. This 3 plus 1 is going to be 4. But we don't care about that. Why do we not care? Because that is outside of our limit. If we know that the target is going to be greater than 3 or less than -3, then we will never get to that target value, right? There's no way, if the target was, say, we want to fill in the slot for a target of 4, there's no way to get to 4 from just these 3 ones. So when we go out of bounds, we can guard that and safely ignore all the calculations that were supposed to go out of bounds, because they do not contribute to the final solution at all. And we know that it's not possible to achieve those solutions. So it's possible for out of bounds, but we don't care because that we know it is impossible to achieve a target that is outside of our limit, right? So what we do is, here I'm just gonna cache the values here, right? Center j minus index and positive equals center j plus nums index, right? Like this is corresponding to choosing a positive and deducting, right? And then this is corresponding to choosing a negative number and deducting, right? Map directly to these choices we have here. Spelled that wrong here, and then so now we can check if negative is within our bounds, right? If it's greater than or equal to 0, and if it's greater than or equal to max limit, then we proceed to filling out this table. And then similarly here, if positive is greater than or equal to 0, and negative or positive is greater than less than or equal to max limit, and we can fill in this slot right here, right? And we also need to account for this. If the initial target it's already impossible, we're going to get out of bounds here as well, right? So what we can do is here we will return 0 if the target actually is going to be, how to say, it's going to be less than our minimum max limit, or if the target is exceeding our maximum limit, then we say, okay, return 0. Else, we return the DP answer here because we know this exists, right? We're not out of bounds, right? So let's check the whole thing here, right? And then let's run this code real quick. Back. Console here, run it. Oh, sorry, I need to call this function as well. DP of noms in target. Target is not defined. Let's see, where does it say that? Target is not defined in line 3. Oh, sorry, this is S. Center of J minus nums index. Oh, sorry. This is not, this is just I. Let's try that. Ooh, output is none. Okay. Okay, figure it out. We forgot to return this DP value here. Haha. But there's also another bug that we found. This limit here, it should also be 2 times the max limit, because if you remember our array, the size is going to do index from max limit times 2 plus 1, right? So it's actually our, and also fill in the indices at the max limit times 2 plus. And also this is unnecessary because we already calculated it, so we can replace the positive and negative values here. And now let's run it. Cool, and then let's try submitting it. All right, it works. There you go, guys. Oh, and also I should probably go through the time complexity, right? The time complexity of the recursive approach, if you look at this tree right here, it's going to be, for each level, we have 2 choices. So it's going to be 2 to the n, right? So the complexity is going to be 2 to the n plus 1, right? Because you have the plus 1 to take care of the base case, right? So if it was 3, so level 1, 2, 4, 1, and your space complexity will just be the depth of the tree. So your space would be the time complexity and space complexity would be just n plus 1, right? Going down that. Your stack is that long, and then for this approach here, our time complexity, right? We do a 2D array, would be n, right? N stands for the array, the number of elements, and times the limit. So the limit here would be, right, the sum of the elements in n, whatever number that might be, right? We don't know that. So that'll be this element times 2, right? And our space complexity, right, also the same, right? We stored it using it essentially a 2D array. So it's the same as the type complexity. And there you go, guys.